Hello and welcome. I'm really happy to see so many in the audience today. Some quick words about me. My name is Theodor and I'm an architect at TV2. I'm located in Bergen. My area is sports and news. So my day job is to aggregate data from outside of Norway and inside of Norway and make it available inside of TV2. So my customers, they are other people inside of TV2. This could be either a very significant election happening in the States kind of soon, where we get data from Associated Press and stuff and present that for the graphics and the news. What I do most is process sports data, different kinds of statistics and analytics and just regular data. We also throw it into the graphics so that when we produce matches ourselves, we get these tickers for, the now it's 1-0 and etc. It comes through our pipelines. So I'll start off with a small showing of hands. How many here has taken down production? Please join me. Yeah, I don't believe you. I believe there's more of you, but sure. How many have done it several times? Only 2. This will be very embarrassing for me. How many have taken down production from stage? No one. Okay. So now I'm alone from here. How many have done it consistently for weeks? Me. Yeah, I'm still alone. That's great. Let's go. This is how it looks like in our graphs. So anyone want to guess what this is? Yeah, you could say it's latency. This is offsets and lag for different Kafka topics that we use in our processing pipeline. Kafka topics. Kafka is a technology where you messaging system or queuing system to send messages through microservices. Simply explained. No, a topic is actually it's basically just a directory of files in order. So you append something to the Kafka topic, and it will be available for other consumers. So there are producers that produce to a Kafka topic. The topic itself is distributed across different brokers and nodes. So you get this replicated, distributed log. And you have consumers that can consume. So you get this nice property of not losing data. At least that's what you want. So if the back pressure gets big, and the back pressure is that the consumer can't consume as fast as the producer can produce. So it's so you get this lag. So right now we're way behind, and it doesn't look good, and it's continuously increasing, which also is considered a bad thing. So what do you do to survive? You scale up because we're in the cloud, right? So we can just bump up the number of replicas and try to process things faster in parallel. That kind of works, as you can tell, from about the same time as this starts going down. It's at about the same time is when we increase the requests there, and we managed to run through the back pressure and keep up with the lag, but it takes a long time. Is that a problem? Yeah, it's a problem because at this exact date, this was happening. I'm sure there are many football hooligans in this audience. Arsenal and Liverpool are 2 very important teams. people care a lot. And also Champions League is perhaps the most important football competition in the world. So it's kind of embarrassing that we are now behind on updates. So I don't have a screenshot from when this was actually happening, but at this point we would just say something like not started during the whole match, which is kind of not good. So I was considering renaming my talk to this. I'll try to win back some sort of confidence, but we'll see. Do you know what this is? This is obviously some sort of system metrics, but specifically this is metrics from our Kafka cluster. So the Kafka cluster is a series of nodes that communicate with each other to append to the log and push and help the consumers and producers to make the data available. And one dangerous signal here is the red CPU. So the CPU is at max, and which is also already pretty bad. But the worst scenario is all the way up in the left corner. The disk is full. So have you had a disk full in some production equipment before? Yeah, that's very bad. So now you can't even communicate with the thing, and yeah, it's really stuck. So now we're in deep problems. You see the small nudge down after a couple of hours at 100%. That's me and some other guys actually just physically deleting things in production just to try to survive. So yeah, why is he not fired yet? We'll see. Okay, so what's this? You want to take a guess? Yes, it says on the slide or screenshot. Yeah, but more specifically, this is our old GraphQL API. So at this point, this is not the same at the same time as the other incident, but this happens quite often. Happened quite often, and what you see here is also auto-scaling, scaling up because the number of requests and the latency and the requests starting to fail, causing us to scale up. So at some point here we run at over 40 CPUs and almost 150 gigabytes of RAM, which is huge. That's extremely much and expensive. Is this a problem? Is it? Maybe, yeah. It doesn't have to be a problem. At least not considering at this time every request anyway times out at 30 seconds. So it doesn't really matter what happens here because we're already dead. So it's considering, another name. So how do you deal with this? How do you get out of this swamp of issues? You tried different ways of examining your systems, your programs, and see if you can find some common but easy low-hanging fruit, to alleviate the stress. There are many tools that can help you with this. This is one, a screenshot shamelessly stolen from Elastic's homepage. APM, I think it's application performance monitoring or something. This will give you a trace, and you can see pretty visually what's going on in your system. This can be helpful, but I've yet to actually discover and fix a bug using this. And the main problem for me with this is that it's sampling based. So if you're lucky, one of your failing traces will be visible, but most of the time it won't. You can of course set the sampling rate to 100%, but then you'll be quickly shut down by your DevOps team for overloading the systems there. I said I took down production from stage. And how would that be possible? There are several ways to do it. One is to, of course, share infrastructure between your environments, which we kind of did, which isn't a really good idea. But so if the disk is full and you use the same Kafka cluster for both, yeah, you're having issues. But what's more interesting is to actually take it down, because now you're using so much internet. Your throughput is so high that you're taking down the whole VPN for the whole organization. So yeah, that's a good way to do it, like DDoSing ourselves. So sampling-based tracing is, or performance monitoring in general, is, in my opinion, useful, of course, but it has some very important limitations. You're at the mercy of the sample. So many of the things that you try to figure out are left out. You can't even find them. So how do you deal with this? You probably have time to read part of this, but this is the first mail from Andres Freund, maybe. He says that the XZ tarballs have been backdoored. So this is the first mail from him earlier this spring for the quite famous vulnerability that was found in SSH. In the next mail, he says, to analyze, I primarily used perf record Intel PT UB to observe where execution diverges between the backdoor being active and not. How many here have heard about Intel PT? 1, 2, 3. Nice. And you'll see some really nice things. Let's figure out what it is. We go to the manual, chapter 33. Intel PT is short for Intel Processor Trace. And this is a hardware feature inside every Intel processor since the Broadwell era. So around 10 years, for the last 10 years, every Intel processor has this. So what it does is that every instruction that passes through your processor will be recorded by the CPU itself, along with some. I'll show you the packages after a while, but it will record some additional information about the processor state and other things. And you can now query this, so you can get a snapshot of what happened. What did your program actually do? So in contrast to sampling-based tracing, you now get a proper execution trace. So you can attach this to, for example, a program that's segfaulting, and it segfaults. And at the segfault, you can just snapshot the trace, and now you can see what happened in the whole operating system, all the way down to the crash, which is an amazing superpower. Not only that, it basically reverse engineers every app you trace, which is also kind of cool. So how does it do it? Every instruction listed on this slide here is emitting a package inside of the CPU. So you get, for example, the jumps, the call, and the rats will record some information about the state and present it. A package can look like this. So you get the header, which is just a signifier of what kind of package this is, and a payload. What's really smart about this is that you get super dense, super compacted information. This is a TNT package, which is a taken, not taken, which shows if a if or else is taken or not. And it can represent it in 1 bit. So it can use a short format, where we have the header is just 0, and you can get a sequence of 6 taken, not taken. And it has a long format where you can get 47 or what it is. So that's if you have a huge function or something with if blah, blah, if blah, if blah, if blah. You can just get it in one package with bits just explaining where you're going. This type of tracing has some limitations. One of them is that it produces huge amounts of data because processors are fast. So there are a lot of things happening. So it has a system to kind of just, if it's overloaded, if too much is happening, it just throws it away. I think you'll probably see it in some examples later today. You'll get this overflow package, which it says, I'm giving up, I'm not doing it anymore. But it has this packet stream boundary packet, which is a certain pattern. All of the zeros and ones, and alternating in the end. This is a pattern that isn't visible any other place in the processor trace. So this is a place where if you have a period where your CPU is overloaded, you can synchronize again. So the decoder of these things can just look at this pattern and say, okay, now we're back on track, so we can continue our trace after it's been overloaded for a while, which is, a nice feature. So how do you use it? It's available in perf today. You can just run it at almost every executable in your system, at least if you have debug symbols somewhere, which will help. So you run perf record, I output it to a file, and I supply Intel PT. I give it some options, which in this case will ask Intel PT to sample or to do a snapshot every cycle, every processor cycle, so as fast as you can. I run it at ls, and let's see what we get. Ta-da! There we go. So that's it. Yeah, it's not. Perf has the script feature, which takes a trace and transforms it. You can do a lot of transforms by yourself, but it has some inbuilt. You have the instruction trace disassemble, which takes the trace and produces the disassembly for the whole trace. So I know it's small, but it's not important. The thing is that this is a loop, at least it looks like it to me, a loop of parsing arguments to the command line of ls. And you can also get a call trace, because in the packets from the trace, they record things like addresses. So where are you returning to or calling into? So now your application is suddenly traceable. So we can see here we run the DL main, and it's doing things. I added also the IPC, instructions per cycle, which shows an estimate of how many instructions you have executed per cycle. So you can get some really granular information here. Yeah? Oh no, go ahead.
Is that the symbols we see here? Is that available, or you have to put like a debug with debug symbols?
It's easier, of course, if you have the debug symbols. But on my system, regular Ubuntu, it was available. So.
This is also the libc startup.
Yeah, this is libc.
Probably has symbols available.
Yeah.
In this case, it's the object LV.sl. Yeah.
That's right. Okay, so I'll just give you a second to read. So have any of you been nerd sniped ever? Yeah, now we see some hands. Yeah, I was nerd sniped real hard a couple of weeks ago. Really hard. And the thing was, this is a file. And the task is, this is a challenge called the 1 billion row challenge, which was going somewhere in this winter, I think. Have you heard about it? Yeah? It's very fun. You get a file on this format. You get a city and a temperature. The format of the temperature is pretty simple. It's either, it has 1 decimal, and it's either positive or negative. And it's split by, and divided by the semi. So the format of this file is pretty simple, which also gives us an opportunity to showcase how to use Intel PT in action. Let's see. So I wrote a program in Zig to solve this. I'll go through it. Is it too small? Can you see it? The people in the back. Yeah. Just shout if I should increase the size of the text. Okay. I'll gloss over some of the details. They are just setup of threads and reading of the file and these things. But the task itself is really simple. It's just you take a file, read it by line, split by the semi, and you get this city. So you parse the string for the city and the float, and you aggregate all the things, and you just mix it. There's a small catch that in the task you're supposed to get the minimum value of each city, the maximum value of each city, and the mean temperature for each city. So now you need to keep some state to figure out what's actually the correct numbers here. So the logic is pretty simple. So I won't go through it too much, but the challenge here is it's 1 billion lines. So suddenly all of the simpler ways to do this is thrown out the window. So the naive version runs in like 3 minutes or something, where you just read line split and do things. It takes a lot of time because it's so many lines. So what do? I just read byte per byte, and if I get the semi, I slurp the name. So I just keep that in mind. And afterwards, I go through the check if the number is negative, and I do some maths. And when I've got it, I just insert it into a string hash table for lookup later. And if it's already existing, I do the min-max mean thing and spit it out. In the end, I join up all the results and print it. So let's just run it real quick. So this is the, I can do it a bit bigger. So this is the result for this small file. The only interesting thing here is Istanbul, which is the only city that occurs twice. So we get 2 temperatures, so we get the min, max, and the mean. All the others aren't that interesting because, they are only occurring once. So let's trace this and see what's actually happening inside. Okay, so that's it. I already traced it. I ran it in the big file. And you can see that perf has already taken a snapshot of 8.5 megabytes. So that's quite a lot of data. And it now has to decode all the things. So now we need to look up all the symbol tables and try to map all these packets and instructions to actual useful data, which takes some time. And we can now plop it into a really nice tool, which is called Magic Trace. This is a tool from the people at Jane Street, a high-frequency trading company from New York. This is actually, it is the Fuchsia tracer, I think, the Google OS, I don't know too much about that, but this is a modified version to get even more granular tracing than that. So these 8 megabytes, they are now 239 megabytes. So I hope that we will be able to render this right now. Otherwise, I'll have to try to take an even smaller snapshot. Let's see. Okay, seems it worked. Yeah. So, what do we have here? We have, is it too small, by the way? The text is going to be small here anyway, so yeah, just bear with me. What we can do now is to examine this trace. So the interesting part of this trace is happening not in this huge block here. This is just a bit of noise. But if you watch really closely, down here on the side, come on, show me. Yeah, there you are. So here we go. So we have a trace. Okay, so now we're down at one iteration of a line, which in this case took 500 nanoseconds, which is, fast and slow considering. But what's really cool is that now we can actually watch and see what happened. So we did the slurp name, which I showed you real quick, and slurp temperature, which is also a thing. And we do the hash. So we do the string context hash and the equals. And this is happening quickly in a loop. We have two traces, two instances of it here, and one really big one, which coincides with me just killing the application. So you get this really big trace in the end, which isn't too interesting. Apart from, you can see, watch the cleanup. And oh yeah, here we have some more traces before we die. So as you can tell, you get pretty granular results here. So yeah, this is us looping, which is pretty awesome. You can, if we're lucky, you can see these outliers. What are they? So this is a page fault. So this is my application just having to do stuff to fetch more data. And we have this. This is a timer interrupt from the time sharing process scheduler in the operating system. So you can actually see that this takes quite a while and gives us these context switches, and takes time.
So presumably, if you peg the process to a core, you wouldn't get that interrupt.
That's right. Yeah, and in traces with only one thread, you likely won't either, because there's no context switching going on. And you can actually see here that from each page fault to page fault, it takes around a millisecond. Pretty consistently, every millisecond we get a page fault, which is interesting. And also every millisecond we get this scheduler timeout, which is something I didn't know. I had actually no idea that that's how it works inside of Linux. So we can see some issues here with the code, of course. We can see that we spend the majority of the time doing the hashing. So the quickest way to optimize this would be to make a better hash or a better data structure or something, so that we don't have to spend so much time on these lookups. So that's what I did. I made a different version where SIG has a really nice feature where you can supply this other way of hashing. So you can just give it a context, and it'll get the hash function and the equal function. So I invented a terrible but functional hashing mechanism for this task. You get a U32 in, and you just pass it through, so you don't do anything. And the equals is just a comparison of two U32s. So that's also very fast. During the parsing of the file, while I read the bytes, I per line just accumulate the key. So I do this very safe and secure key algorithm, which cannot collide ever. Of course it can, but it doesn't in the dataset, so I'm fine. So I just multiply the key with 31 and add the character for good measure. So now we don't have a string map to do the comparisons. So everything else is the same. I do the same getter put and yeah, everything. So let's run this, and let's just confirm that it still works. We get the Istanbul with the mean and yeah, whatnot. And then we do the trace. Yeah, so it's still 8 megabytes. Hopefully we'll be fine. The magic trace application, it dies when the trace is too big. So it expands to something like 2 gigabytes of RAM in this thing, and it's just, yeah, can't handle it. So hopefully we're fine. But this, unfortunately, takes a bit of time. Any questions while this runs? Yeah, in the back? Yeah, so the question is there anything similar for ARM? There is and isn't. There is something that looks the same. I don't remember the name of it right now, but it doesn't have the same tooling as for now. But hopefully, yeah, we'll see it in a not too distant future. Did it finish? Yeah, so it finished.
Excuse me.
Yeah, no worries.
So this magic trace software, that's like it uses the raw data from Perf. Is that correct?
Yes, it uses it's an application written in OCaml. It uses the raw data from Perf, and it just transforms it to the format that's used in the Fuchsia tracer from Google. So it's quite simple transformation. But yeah, that's basically it. So let's see if we can find the trace now. So here we go. Okay, so we see we still have the page faults and the timer things, but we haven't addressed that yet, so that's not a big concern right now. But we can still see that we do the same. The algorithm is still the same. We do the name and the key, temperature, and then we do the hashing. But now this is much less going on here now. The hash function itself, it's this one, and it takes 1 nanosecond, which would now, with a billion lines, this would account for 1 second of the whole processing time, given that you do it in one thread. The same thing applies for the equals. It's 1 second, 1 nanoseconds as well. So now we're pretty good on the time here. Yeah.
Is it actually 1 nanosecond, or is that just an artifact of it snapping to a sort of smallest addressable time unit?
Yeah, it's the question was, is this actually a wall clock type of nanosecond? Did it actually take this much time? The answer is yeah, kinda. The answer is that it did in general, but because the Intel PT tracing is a bit inaccurate in some manners, it uses a combination of a wall clock and CPU cycle calculation. So in general, I think you can just consider it as a one-to-one in the timing, but there are some edge cases here that deeper reading into the manual is required to really understand. But now we're getting better here. There are less things going on. But we have these page faults and these timer events. So we need to get rid of them. And that's actually pretty simple. What we do is we do, it's 4. We do, in addition to the memory mapping of the file, a mapping of the file that we have done already in the other examples as well, we now use madvice. So now we just tell the operating system that, yeah, I'm going to read the whole thing, just give it to me. Just be prepared. I will read it. In addition, there's another change here. As you can tell from the comment, we know the name start and end, and now we aren't using the name as the key anymore, just using the int. So there's no need to calculate it for all the billion lines. We only need to calculate it on the first insertion. So the first time we see a new entry, we have to calculate it. So that's what we did. So that reduces the amount of times that we get this name from 1 billion to 413, which is also a very nice optimization. It looks like you have a question.
So the hashing and the equals algorithm was 1 microsecond now?
Nanosecond.
So what was it before? I kind of missed that.
Yeah. So I'm sorry, I didn't actually show it to you. It's around 500 nanosecond each. So you get a lot of it. Yeah.
It was a big improvement.
Yeah, huge improvement. I should have shown that. I can do it if I have time afterwards. One thing to keep in mind is that this is running a debug build of SIG. So right now we haven't enabled all the optimization that the SIG compiler can do anyway. So the timings here are a bit, we can do better just by upping our compiler. So yeah, let's run this. So make run. We are still good on the result, which is nice. And now let's do the trace. Yes, I got a smaller trace. So it'll take a bit shorter. I can see if I can also show you the cleanup of the application while this is doing its thing. Yeah, so when the main thread dies, we also get to look at how it cleans up the memory mapping. And so now you can really dive into what the kernel is doing and what the application is actually doing while cleaning up, which is also quite interesting. So this opens up a huge amount of possibilities to dig. I think you can still zoom. Yeah, it's just struggling with the size of the thing. So now we're really down in the nitty-gritty. So these are the couple of nanoseconds in one iteration of cleaning up the memory mapping. So this is a great place to find page faults and all sorts of fun things that's happening in your application. And I think this is amazing to just zoom out. Oof, now it's struggling real hard. This is probably also a page fault. So yeah, and how is the trace? Yeah, it's done. So let's get the last one. Okay, so it seemed like it didn't work, which is really interesting. Seems like we still get the page faults and still get the system timers. And we can fix that, but let's just look at the rest of the thing. Now we can see that the name is gone. So there's nothing happening now for the name. Everything else is still the same. So how do we fix these interrupts? Let's do I think it's make fast. Yeah. So let's trace the fast. Now I've just compiled it with optimization release fast. Yeah. it's faster, so now it was able to collect more stuff. Yeah. But I'm not sure if you noticed, but the decoding was faster, which is kind of strange, maybe, but we'll get the answer to that pretty soon. So now let's zoom out a bit and just find everything. Yeah. Come on, do your thing. Yeah. Okay, so here. Nope. Yeah. Now this is the code. I'm not sure actually why the interrupts and are still happening right now. Probably it's because I'm sharing my screen or something. But what you can see is that the code is gone. There is no longer any code executing. And that's because everything is optimized away. So now everything is inlined. All the stuff is gone. So it isn't happening anymore. None of the package is sent because there's nothing to send. The application now is so highly optimized that there are very few packages that we trigger. We trigger no calls because everything is inlined. We trigger no returns because everything is inlined. And the ifs are probably just conditionals are optimized away. And so now it runs very fast. So I think I have the run fast. So if we're lucky, this will work. Yeah, so now it took 2.5 seconds to run through the whole billion line file, which is kind of good. From the challenge, one of the best results there was at a 1.5 second, and it's running on a stronger computer than mine. So yeah, I'm not sure where this will end up, but it's pretty fast. But it's fun. So how does this relate, if at all, to my introduction with us going down in production? It kind of doesn't, but it kind of does. When debugging these sorts of production issues, we have faced a lot of problems because a lot of it isn't really visible. Much of our stack uses technology like Spring Boot with Java and other frameworks and other magic type of technology. And they offer very little insight, really. Either because they are running on the JVM, which is a bit hard to use this kind of tracing for because of the translation from bytecode. But more so, when you do tracing, even if it's sampling based or if it's execution based like this, in these types of application, you get this enormous pillar in a flame graph, which is that Spring framework, which it's a meter tall, and then you see your own code is like just a tiny spot on the end of it. So the only logical conclusion you can make is that it's not my fault, right? Because the application it's not me, it's the framework. It's doing its thing, and these people are definitely smarter than me, right? These are geniuses writing these super frameworks, and I'm just this little dude from Bergen. So who am I to really question what's happening? So it leads into this spiral of conclusions that are really wrong, in my opinion. And I'll show you one thing that we did using Magic Trace in the process to alleviate a lot of this pain. I wrote a library in Go. It's super simple. So one of the tasks that we do is that we persist some data to a database. And then we want to fire that event downstream to some other listeners. So we want to communicate some event, or we want to store something and ship it for some reason. We've used a technology called Debuggers. It's not really relevant to name it, but it's called Debuggers. This is widely used, quite optimized application that uses Postgres's write-ahead log. So if you write to persist to the database, you can get a log of what happened in a transaction. So you get these nice benefits of knowing the order of what happened when and all of these things. So you get this guarantee. So you get to avoid the double write problem, where you try to persist to a database and you try to send something to Kafka. One of them fails, and now you have inconsistent state. So you avoid that using the Debusium. The problem is that it takes almost a second per message for Debusium to do its thing, which is a lot. At least I think it is. So I just kind of made my own Debusium. This is using a different technology from Postgres called listen notify. Have you used it? Anybody? No. It's just a very simple thing. You register a function inside of Postgres, and you just say, if this happens, just shoot a notify. And you can have listeners. So you can make Postgres just fire out an event to you, and you can listen to it and act accordingly. So what this application does is that it starts up a service with some handlers that can just that you configure yourself individually per application where you use it, and you can just sit and wait. So the listen method function itself is doing this. It says wait for notifications. So you're sitting like a dog waiting for a treat with an open connection to the database, and just right. And so when something happens, you just take it and fire it back into Kafka as quickly as you can. And it's not really more to it. That's what we need, and that's what we made. This took me 4 or 5 hours one day to write. It's like 200 lines of code. It's really nothing. So you don't have to be smart. You don't have to be, one of these huge framework geniuses to make this. It's just very simple. You just have an open connection and poop it out. And yeah, so I'll show you how it works. To do that, we need a whole Kafka cluster. So I'll fire up a Kafka cluster of with three nodes. And just a second. There you go. And we will fire up the application as well. I'll trigger 2 messages, and we can just watch the latency. It'll take some seconds to do its thing. Creates the topics. It starts up the thing. So soon it'll tell us that it's listening. Yeah. So now I start magic trace again, tracing my application. So now it fired 1 event, waits a couple of seconds, and fires another one. So let's stop magic trace. And so these are the 2 events. Let's go back into Emacs for a second and just look at the timestamps here. So Postgres reports, and the first event was written 250 milliseconds into this second, and 5 seconds later, it's at 287. That does not correspond to this. The first here, so that means the first event here took 750 milliseconds. But the second, from 287 to 293, so that only took 6 milliseconds. Why? This is really interesting, because this shows what kinds of subtle bugs you can find with magic trace and Intel PT tracing in general. So let's look at it. Okay. So the reason I did the example first is because we could just run that in one thread, and the code is simpler. So it's it's more easy to get a feel of what magic trace looks like. But now we're running in many threads, and it's sorry, I just have to find the correct trace. Samples app trace. So this is it. Okay, so we can now see that the first producing here is doing all of this authentication stuff, SSL. So every time we see SSL inside of this application, it means that we are re-authenticating. So we are spending a lot of time handshaking with the Kafka cluster to establish our connection, which takes a lot of time. Is that a problem? It might not be, but it is, because this happens every between 5 and 10 minutes. So it means that if we have an idle time in our application, now we're likely that we will get a latency penalty for the first thing, which is unacceptable. So how do you deal with this? I can try to find the, just for to make a point of it. I can try, no, I don't want to spend time doing that. The second one we saw is really quick. It's because it doesn't do any of the SSL things. So we do make new. Just give it some time. Emacs is fun because it can't handle this fancy Docker Compose thing, so it just has to print it out as fast as it can. Okay, so we're building the application. And soon we're listening. There we go. So first event and second event, and I'll stop the trace. Okay, so let's look at the timings again. The first one was 7:53, which is now 7 milliseconds. So we won. The other one, 7:84, is now 7:89, so that's 5 milliseconds. So we managed to do both of them, which is really nice. So what did it do differently? Let's take a look. It's so nice because now you don't have to even read the code anymore. You can just trace it and figure out. Sorry, it's a handle. No, yeah. So this is it. This is it. Yeah, so it's 30 microseconds of processing now. Why? Now this application, firstly, it's using a different Kafka library, which helps. But more importantly, now we're issuing heartbeat events to the Kafka cluster. So we're just ensuring that we stay awake. So it's no big thing. The solution isn't really, wow, that's super impressive. It's actually very simple. It's just don't do the bad thing and do the good thing instead. And this is very visible using this kind of tracing in a way that I haven't seen before. And you can find these super subtle bugs. Well, this wasn't really a bug, but it was a problem nonetheless. So let me go back to here. Yeah, so we have the snipe slide. And yeah. So compared to the other graphs I showed you in the beginning, now this is a tracing for, I think it's a couple of days, yeah, just recently. You can tell, as you can tell, we still have some outliers around, yeah, a second, but it's never, 3 days anymore, which is kind of nice, I can tell you. But more importantly, we can see that the hotspots here are all situated around 15 to 20 milliseconds, which is kind of good. We're not high-frequency traders or anything, so it's not super important. But more importantly, what does this do to your whole infrastructure? It's probably impossible to read, but on the top right, left side, hand side there, it says $800. So this is the cloud costs for our services combined, and rewriting the things into this kind of simpler, super simple architecture has reduced the cost from around over $800 a day to soon under $200 a day, which amounts to something like 3.5 million kroners a year, which is kind of impressive, at least considering that would be a 70-80% decrease in cloud costs. Another pretty nice thing is that this application, it hasn't had a bug yet, not one. It hasn't had a production issue, and it was written in just a couple of hours. And I hope that kind of inventiveness will persist longer than this addiction of using these frameworks and libraries that we don't really understand, we can't really inspect them, and we have no idea what they're doing, and we accept that they're there to stay and was made by these geniuses that are much smarter than us. And they might be, but they're not working in my team with my things. So it's impossible for them to actually make something that's better than it is for us to do it. And I said it had no bugs, and that's also not because we are good or anything. It's just because it's 200 lines of code. So if there is a bug there, you can fix it in 5 minutes. It's not a problem. It's not 15,000 lines of magic Spring configuration auto annotation thing, right? Which is also a huge benefit. So I really hope that as a bigger message than what I've said earlier, this also actually ties into the talk besides us. I think I haven't heard the talk, obviously, but it's talking about green computing. This is reducing cloud costs to almost nothing. Every single one of these applications that we used earlier is spent around 2.5 gigabytes of RAM, and was idling on one full CPU at a time, all the time. These applications are running at 5 megabytes of RAM and idling at 0 CPU. It's nothing. So you know, now you can suddenly understand what you have, and you don't have to pay almost anything to Jeff Bezos anymore, which is also a huge benefit. So to me, that's magic of a trace. Thank you.